Okay, welcome. In this video, we're going to discuss our week 6 material. In particular, we will discuss linear approximations as an application of derivatives, maxima and minimas, and we'll also talk about continuity and the intermediate value theorem. So our story starts today with linear approximations. So a linear approximation is very nice because it takes a curve that we have. So maybe this is our curve here, and the curve might be difficult to calculate things on. But if you use the method of linear approximations, you get a tangent line. So if that's our tangent line, we can actually use the tangent line to estimate values that are close to the tangent point on the curve. So the idea is that it may be maybe not so hard to calculate the point that's on the line, but it might be kind of tricky to calculate the point that's on the curve. And this is, of course, an approximation, but it's a pretty darn good approximation because the line does approximate how the curve reacts, at least for points that are close to the tangent point. So let's look at an example. Let's see how this works. So first we have a function. This curve looks kind of ugly, kind of tricky to calculate things on, and certainly you're getting like exact sort of ugly numbers that are e to the negative power and squared. Seems like quite a tricky task, especially to do by hand. So we're going to create a line that gives us a linear approximation. So the first thing that we're going to do is take the derivative of our function. So we take our derivative, we get to copy the exponential function once again. So there's our copied exponential. Then we have to take the derivative by the chain rule of the power. So the -2 comes down, and then we copy what's inside the brackets. And then we raise things to a power of 1 instead. So that power of 1 just goes away, and the derivative of the inside is just 1 as well. So that's the entire derivative. And we would like the slope of our tangent line at the point a equal to 1. So I'm going to go ahead and plug in 1 to our derivative and see what we get. So in the power, we get a -1. So it would be e to the power of -1, then multiplied by -2, and then multiplied by 1 minus 2, which is -1. So all multiplied by +2, giving us 2 over e. So that is the slope of our tangent line. The final ingredient that we need is a point. So the point is given to us directly with the question that a is our x value, and if we plug in a to our function f, we'll get our point itself. So a is 1, and then to plug in our point, we'll get e raised to the power of minus, and then plugging in 1, we get 1 minus 2 all squared. So the point turns out to be 1 comma 1 over e, because we have -1 in the power once again. So we have a point. Let's get our red pen out here and just kind of indicate what we've done. So there's our point, and we have the slope from above. Anytime you have a point and a slope, you can build a line. So we're going to go ahead and do that. So our slope of our line is 2 over e, and then I'm going to write all this down on my page. And then I just have to write in my x-coordinate, which is 1, and my y-coordinate, which is 1 over e. And this builds us our line. This is, in fact, the tangent line of our curve at a equal to 1. And it has a special name called the linearization of the function at this point. So we're using the tangent line for the purpose of approximation. And then when we're using it for this purpose, we call it the linearization. And our linearization will work for values that are close to the tangent point. So the idea is that the function is rather difficult to calculate things, kind of an ugly looking function, but we can estimate, we can give it the squiggly equal sign to instead get L of x, and this is 4 x values, so 4 x values that are close to 1. So close to the a equal 1 value. So let's see if we can deal with these values right here. So let's try to find out what those values might estimate as. So let's write down the first value on our page, e to the power of minus 0.81. Okay, and they were kind to us because we know that we need to build a square of something, and they gave us 0.81, which is 9 squared. So I'm going to write e to the power of minus 0.9 squared, and I'm going to have to subtract 2, so I'm also going to have to add 2 because I don't have a minus 2. So if I'm going to add 2 to this number, I want that number to be close to 1. So if I just added 2 right now, maybe that's not going to work so well because then I would have 2.9, and I'm looking for a value that is close to 1. So I'm not so excited about that. But what we can do here, a little bit of a trick of the trade, I'm squaring, so I can also consider like the plus or minus inside of the brackets. And I was just considering the plus version before, but right now I'm also going to switch over and think about the minus value. And if I'm going to add 2 to minus 0.9, that will work out perfectly because I'll get 1.1, a value close to 1 as I'm looking for. Okay, so now comes the time where I get to add 2 and subtract 2 in those brackets. So I have e to the minus 1.1 minus 2 all squared. And now I've built exactly my function. So my function sitting right here has been built in a numeric format below. So this is equal to my function evaluated at 1.1. And the good news is we can get an estimation now. We can use this estimation to transfer over to our linear approximation. So I'll write a red squiggly line because this is the special step that we get to transfer over to L of 1.1. Okay, and luckily enough, the L is still right on the screen there. So I can just go ahead and plug in the value 1.1 to that line. So I get 2 over e, and then x minus 1, so 1.1 minus 1 would give me just 0.1, or how about we write 1 over 10, so we can write everything in terms of fractions, and then I'd write 1 over e. So this all boils down to 12 over 10e. So the idea is that this number should be a very good estimation of this number. If we plug that into a calculator, we should get some estimate that actually works. Okay, we're going to try one more example, very similar to the one that we just did. This time we have e to the minus 1.21. And I suppose they were nice to us again. They gave us the square of 11. 11 squared is 121. So I can write this down as e to the power of minus 1.1 all squared. And this will allow me to add 2 and get a function value that is close to 1 again. So if I take e to the negative power and I add and subtract 2 within those brackets, this time I get 0.9 minus 2, right? 0.9 minus 2 will give me minus 1.1. So this is exactly the function evaluated at point 9. So red squiggly line will take me over to my linear approximation of point 9, and my linear approximation this time will be 2 over e, and then inside of the brackets I would get minus 1/10, and then plus 1 over e, and if I add this all together this time I will get 8 over 10e. And that should be a very nice approximation of the number that I started with. Okay, so here's another function. So we're given a function and an a value, and we want to find the linearization. So my derivative of my function is 4x cubed plus 6x, and then I'm interested in evaluating a specific slope at -1. So I plug in -1, and I get -4 minus 6, so the whole thing is -10. So my slope is a sharp downhill slope of -10. And the point that I'm looking for, we can again use a comma f of a, and -1 can be my x value, and then plugging in -1 to the function itself gives me 4. So we're all set to write out the linearization again. So L of x is -10 multiplied by x minus the x-coordinate, which is -1, and then plus the y-coordinate, which is 4. So if we do a little bit of simplification, you'll find that C is the correct answer here. So we do -10 plus 4 to get this -6 that's sitting there. All right, here's another example. So this time we have our derivative as 1 over x. And then we'll go ahead and plug in the a value that they gave us, which is 1. So 1 over 1 just gives me 1. And then the point, a comma f of a. So this time around, that's equal to 1. And if I plug in 1 to the ln function, I just get 0 out of the deal. So I have all of the items that I need to make my linearization. The linearization is 1 as the slope, so 1 multiplied by x. I don't even have to write that. And then minus the x-coordinate, and then plus the y-coordinate, that's just plus 0. So that can all go away. And you, of course, don't need to write the brackets here. You can just write x minus 1 as in the answer for part A. Okay, so that covers some examples for what we call linearization. So the next thing that we want to talk about today is continuity. So if you have a continuous function, it means that as you're writing your function down on your page, you're not lifting your pen. So you're not making a jump like that. You're continuing along the page in some format so that it's continuous. So this would be an example of maybe a function that's continuous from 0 to infinity. So there's some different ways that discontinuities could come up, and we'll talk about those in a moment. I just want to mention that most all of the functions that we're dealing with are continuous on their domain. So if you write down a function like x squared plus x, this is what we call a polynomial. The polynomial is continuous everywhere on all real numbers. But even if you make it into a rational function, so let's say you divide it by x minus 1, so now, okay, you might get a vertical asymptote here, but you can still say that it's continuous everywhere on its domain. So everywhere that this is actually defined, it's continuous. So often those two notions go together. Where it's defined is actually where it's continuous. And that occurs for a lot of different functions. Almost all the functions that we work with in this course are continuous on their domain. So trigonometric functions, rational functions, polynomials, exponential functions are all continuous on their domains. Okay, so what can make a function discontinuous? There's three types, and I'll go over those three types with you now. The first one is called a jump. So you can have a jump discontinuity if your function goes along and it sort of jumps to somewhere else in a different vertical height. So that's what we call a jump discontinuity. We can also have an asymptote or an infinite discontinuity. Anytime you have a vertical asymptote, you get a discontinuity. So I'm going to call this an asymptote, but I've also heard it called an infinite discontinuity. So another way to describe it is just with the word infinite. Okay, and one more type of discontinuity that could occur is a removable discontinuity, or sometimes also called a hole. So as you're going along, there's just a hole in your curve. There's one point that's been removed. So it's kind of a natural name, either a hole or a removable discontinuity. Okay, so we were discussing all the different types of functions that are continuous. So I'll just kind of discuss them one more time. You can have trigonometric functions. You can have polynomials. You can have rational functions. So that's a polynomial divided by a polynomial. So something that looks like f of x over g of x, where f and g are polynomials. Exponential functions. So these types of functions are all continuous on their domain. So it's not that they don't have a point of discontinuity. I'm saying they are continuous. So continuous on their, so specifically to these functions, domains. So anywhere they're defined, they're also continuous. Okay, so we're supposed to decide if the following function is continuous. Okay. And specifically at 2 pi. So what you can do is you could just plug in the point, like 2 pi, and just see what happens. So if we plug in 2 pi, we get 1 over 1 minus sine at 2 pi. Okay, and sine at 2 pi is 0. So you get 1 over 1 minus 0. So this is just 1. We get a value, so it's in the domain, so it is continuous there. Okay, but I also want to discuss ways that this could occur where we might get the discontinuities that could appear above. So we know what they look like from above, but what actually happens algebraically? How would we create such discontinuities? So I'd like to go through kind of each of those possibilities. To get a removable discontinuity, what you'd want to have happen is your function evaluates to like 0 over 0. So if I was to create a removable discontinuity here, what I could do is like multiply top and bottom by the same factor, let's just say x, that would create a removable discontinuity at 0. Okay, now, what about a jump discontinuity? That would come from something like a piecewise function. So you have a function that's defined one way on part of the real interval, and then another way on the other part of the real interval. So a piecewise function is certainly one way that you can get a jump discontinuity. Okay, an infinite discontinuity, you may have already kind of thought about how this can occur with our discussion on limits. Well, if you have a number that's actually non-zero, so if n is not 0 and it's being divided by something that's 0, then you would have a infinite discontinuity. So these are 3 different algebraic ways that you can make discontinuities. So for example, if this above function, if I change that to cos, if I change the sign to a cos, right, cos at 2 pi is going to equal 1. So then you'd have like the format of 1 over 1 minus 1, which would give you this format of 1 over 0, which is going to produce a vertical asymptote, which is going to produce what we call an infinite discontinuity. So the question didn't ask for every single one of those details, but I thought I'd go over the other possibilities. Okay, so here's a very popular calculus style question that comes up. So for which values of b is the following function continuous? I see this type of question on first year calculus exams all the time. So what you have here is the square root function. So if we just let me draw that, but it's only defined until 1. And then at 1, instead of listening to the piece about the square root, we then start listening to the piece that is 2x minus b, which creates a line. So we have some line. Our job is to make sure that that line, so this part of it actually matches up with the curve so that it is continuous. If we pick any old b, it's probably not going to be continuous. So I'm just going to write on this line that this is my 2x minus b line, and on the curve here, that's root x. We need to make the two match up. So how do we do that? Well, we'll look at the point 1 and see if we can create the scenario so that at 1, these two functions match up. So what we need to have happen, so we need this function f, we need to have it evaluated at 1 to the same thing as the limit evaluates at 1, and I suppose we're only really interested in the limit from the right-hand side. So as x approaches 1 from the right, because we can see that as we go from the left, we're already continuous to the point 1. Like we already hit the point 1. But what we have to do is make sure that line also hits the point 1. So I'm interested in what happens from the right-hand side as I go closer to 1 for this function. Okay, so f at 1, if I plug in 1, I get to listen to the less than or equal to 1 part, and I just have the square root of 1. And on the other hand, I have the limit as x approaches 1 from the right-hand side, so I get to listen to values that are bigger than or equal, strictly bigger than 1, not bigger than or equal to, excuse me. So I have that limit evaluating, which is plug in 1, because there's no reason why I can't just plug in 1 to evaluate that limit. Okay, so I need 2 minus 1 to equal 1, so my b value should equal 1. So D is the correct answer, and what that's going to do is allow me to adjust that line so that it fits right into place how we want it to fit. And I'll just fill in that circle so it makes sense. Okay, so here's another discussion about how to design continuous functions. So the first part is a statement. It says that if f is continuous at g of a, and g is continuous at a itself, then we can make a conclusion that the composition is continuous at a. Okay, so let's see an example of how that would work. So below we have h of x equal to the square root. So maybe we'll call the square root function f. So let's just say f of x is the square root of x. And then what do we put underneath the square root? Well, we'll say that that's g. So g of x, maybe we'll write that over here, g of x is equal to x over x minus 3. So my function f of x, thankfully that's a function that I can draw nice and easily again. It's the square root function. So it looks something like that. And I'd like to also draw g of x so I can decide where it's continuous. Now I have a little bit of trouble drawing it directly, but if I use a little trick up my sleeve again, if I notice that the denominator looks really close to the numerator, and if I subtract 3 and pay the penalty by adding 3, what I can do is shape this function to look a little bit more like a function I know. So now if I subdivide the denominator into the numerator, I would get 1 plus 3 over x minus 3. And the reason why I'm doing this is because now it looks closer to the function y equals 1 over x. And that's a function that I know how to draw. It's just been transformed a little bit here. Okay, so let's try to draw this one. So the function y equals 1 over x looks like this, but it's been shifted first. It's been shifted up 1 unit, so that asymptote is now at y equal to 1. And then there's a vertical asymptote that's usually right on the y-axis, but it's been shifted to the right by 3 units. So that line is x equal to 3. And then the curve was also compressed by 3 units in the x direction. So we end up kind of looking something like this. It may not be perfect, but it doesn't have to be perfect. This looks something like that. Okay, now the important thing is to read what it says above. So we just have to look where f is continuous, and wherever those values where f is continuous, we can look at corresponding values of g where it is continuous, and then we can figure out where the composition is continuous. So I'll get out the highlighter, and I'll say, okay, this is continuous everywhere on its domain, so I'll highlight all of that. And of course, it only allows positive values to be plugged into it. So I can only consider the positive values that will output towards a continuous function. So I only allow myself positive values of the g function, which are those ones right there. So my domain, or my section of my function that is continuous, comes from minus infinity all the way up to 0. And there's another section over here on the right-hand side that I highlighted that starts at 3 and goes all the way up to positive infinity. Okay, so if I put those two together, so this part was highlighted and that part was highlighted, I can say that my answer is C to get the section that it's continuous on. There is another way to do this problem, and I just mentioned it. You could also just simply find the domain of this function and recognize that that function is continuous everywhere on its domain, and that would lead you to the same answer. But I kind of wanted to use the rule that they put in front of us here. So that's why I did it in this particular sort of graphical way to show you how that rule works. Okay, so the intermediate value theorem. So this says that we're going to suppose a function is continuous on a closed interval where f and b are not the same. So we have this f value and b value, and there's an n value that's between them because f of b and f of a are not the same. And then there's a little mistake here. I need to write f of a. It shouldn't be between a and b. It should be between f of a and f of b. Our conclusion is that we can find a c value that is somewhere in between a and b. So that part should be on the open interval between a and b, such that f of c is equal to n. So somewhere along a and b, we should be able to find a c value, so right there, so that the function evaluates exactly to n. And this should all sort of make intuitive sense. Everything that we just said might sound a little bit mathematically complicated, but the whole idea is not really all that complicated. If you think of the n value being somewhere above this point, and the n value being somewhere below that point, that's what this says. N is something between those heights. And very key, we're told that this function is continuous. So as we travel along the function, we can't take our pen off the page. So that means at some point, we must hit our target line, our target n value. We have to cross that line at some point. If we start below it and we end up above it, we must cross the line if we're not allowed to lift our pen off the page. So that's all it's really saying. Now there are some nice applications to using the intermediate value theorem. You could also just sort of notice that it could cross more than one time. It could hit that n value like a whole bunch of times, but we know that it crosses at least one time. So let's look at some applications to using the intermediate value theorem. So it might be kind of tricky to solve an equation like this. To find that actual x value might be kind of tricky. But what you could do is say there is a solution within a particular interval using the intermediate value theorem. So the first thing that we will need here is a function. So we're going to build our function by just subtracting x on both sides. So f of x will be x multiplied by ln x minus x. So there's my function. Now that I have a function, I can go ahead and use the intermediate value theorem. The first thing that I want to make sure is that my function is continuous on a particular closed interval. So this is something to just think about and verify. So f is continuous. Just make sure. Is it continuous from 1 to e squared? Well, it is, because the domain of this function is all positive real numbers. Okay, maybe we can't plug in negative real numbers because we have this ln of x, but we can plug in positive real numbers. So we can certainly say that it's continuous on this closed interval from 1 to e squared. So if we start with our pen on the page at 1, we can travel along and hit e squared, with these being x values, of course, without taking our pen off of the page. Okay, so that's point number 1. So what else do we need? So now we need to have a value that is below our target value. So if our target value is n, we need something below it, or something above it as well. And in this case, well, what is our target value? Well, we're looking for a solution to this equation, and we just subtract x to both sides. So we're really looking for this equation to equal 0, or this function to equal 0. That's what we would be excited about. If there's some x that we can plug in that makes all of that equal to 0, we'd have the desired information that there is a solution. Okay, so let's take our function f and plug in 1 and just see what happens. So if you plug in 1, you get 0 minus 1 is equal to minus 1. Okay, there we go. We have a negative number. Now we'll try to plug in the other number they gave us, which is e squared. So if we go ahead and plug in e squared, we get e squared multiplied by ln of e squared minus e squared. So that's e squared multiplied by 2. Remember, ln of e is just 1, so 2 e squareds minus an e squared gives me an e squared. And e squared is, lo and behold, positive. So if we put all of these things together, we can use the intermediate value theorem to get the conclusion that we want. So let's use it exactly the way that it's intended to be used. I'm just going to make myself a little bit more space by shoving this bottom part over a bit. So we'll use these 3 facts. When we do that, I'm going to write these brackets because I'm saying that all those facts get put together, and I'll write IVT by the intermediate value theorem. We can say that f has some c value, we don't know which c value, that will allow us to cross the x-axis. I'm just going to call that a root. That's kind of the nice way to say we're crossing the x-axis. So x has a root, f has a root, and we know a little bit about the location of this root in the interval somewhere in between 1 and e squared. Okay, so therefore we can make the conclusion that we're looking for. So we can say, therefore, x times ln x equal to x has a solution, and it's in the interval that they told us to figure that out. So we're not actually finding the solution, we're just showing that it has a solution. So there's different language there. We're not specifically coming up with the number, but we know that number exists. So I have some fun little representations of the intermediate value theorem. This one says, you're once exactly 3 feet tall. So if we just kind of picture the average type of person, maybe you start at like 20 inches when you're a baby, and then your height kind of You have a little bit of a growth spurt and then it tapers off, and maybe the tapering off point is, let's say, at 6 feet. So this axis here is in feet. At some point in between that, there's a number that is 3 feet. Maybe right there. And the intermediate value theorem says, because we have a continuous function here, there is some age that occurs. So if this x-axis represents your life, when you're some age, you are exactly 3 feet tall. That is a true statement if we're considering your growth as a continuous function. Maybe people don't keep track of that instant in life that occurred, but technically it did occur at some point. Okay, so similar style problem. At some time since you were born, your weight in pounds equal your height in inches. So here's a slightly different approach, but similar idea. Again, it relies on continuity. So if we think of maybe your weight first, so the average weight of a baby is 7 pounds. And then you hit your growth spurt, and then maybe your weight doesn't change as much later on in life. Maybe that's something like 180 pounds. This is just sort of the average arbitrary numbers. But if you then look at your height, as I was saying before, your height as a baby is usually about 20 inches. And then you will grow, and then you sort of taper off at some point, maybe 6 feet, like 72 inches. So the red line is representing inches, while the blue line is representing pounds. And at some point, these two functions cross each other. If one of them goes up to 180 and one of them goes up to 72, of course, every person is a little bit different, but on average, this is somewhat correct, that they would have to cross. So by the nature of continuity, you can say that these two functions will cross each other and kind of create this true statement. And if you wanted to sort of picture this exactly in the same way as the intermediate value theorem, you'd want to do something that we did above, where you take the one function and you subtract it from the other function to get a single function to deal with in the intermediate value theorem. So another way to kind of look at this problem is say, okay, well, this function will cross that function at some point in that interval. But we had to have just one function to work with the intermediate value theorem. So I subtracted the right-hand side from the left-hand side. Okay, so any basketball fans? This one will kind of up your alley, but even if you don't know basketball, that's perfectly fine. I just wanted to throw something in there that would be false. If you're playing the game of basketball and at halftime you hit 36 points, is it saying that there's one moment where the amount of points must be 25? Well, because you can score like 2-pointers or 3-pointers in a basketball game, or maybe 1-pointers if you're hitting a foul shot, you might have not hit 25 points exactly. So in terms of like the integers, this particular idea in life, or this function that would represent the points that are scored in a basketball game, would be non-continuous. So we have a situation here where it's non-continuous. So this particular example is false. And it's just really a reminder to make sure that if you're ever using the intermediate value theorem, make sure that the function you're dealing with is continuous. All right, here's another quick example. that we can do similar to how we did the one above. We're going to use the intermediate value theorem to show that there's a solution, and it's going to look a lot like the example from before. So I have sine x, and I'm going to subtract both sides by x squared and minus x, or add x to both sides. And then my target number that I'm trying to make sure I cross is 0, so I'm looking for a root of this function. And I can say that f is continuous on the values 1 to 2. It's actually continuous on all real numbers. The domain here is complete, so I can certainly say that it's continuous from 1 to 2. And I suppose to be really accurate with the intermediate value theorem, I do need square brackets there. I can start writing a closed circle at 1 and then go towards 2. Okay, so that's point number 1. Point number 2, I need something either above or below 0, which should happen no matter what. I just have to plug in numbers and see what happens. So if I plug in 1 to my function, I get sine of 1 and then I get minus 1 plus 1, so that part just goes away. So it's just sine of 1. Now I don't know exactly what sine of 1 equals, but I do know that it's a positive value. So sine at 0 is 0, and then it keeps increasing until I hit pi over 2, and pi over 2 is more than 1, so I do know that this is a positive amount. Okay, so next I will plug in 2. So if I plug in f of 2, I get sine of 2, and then minus 4, 2 squared, and then plus 2. So all of this equals sine evaluated at 2 minus 2. Okay, and again, I don't know exactly what sine of 2 equals, but I do know that as large as sine can possibly get is 1. So no matter what, even if sine is at its largest value, this expression that I just wrote down is negative because I'm subtracting 2. So I have exactly what I need to put all the ingredients together for the intermediate value theorem. I can state just as above. I can say that f has a root in the interval 1, 2. And I can make my conclusion, therefore the equation has a solution in the interval from 1 to 2. So therefore, I'm going to write there is a solution in the interval 1, 2. And that's what the question asks for. So in quick summary, you have your x-axis, which is representing the n value in the intermediate value theorem. And we have found a point that is below and a point that is above the x-axis. So I guess first we found a point that is above. So when we plugged in 1, we got a positive value. And when we plugged in 2, we got a negative value. And because it's continuous, it has to cross somewhere. We don't know where exactly, but it has to cross somewhere. Okay. So that gives you a good impression of what we call the intermediate value. Okay, so next we'll move on to finding maxes and finding minimums. So this is another application to derivatives. And the first thing that I'd like to mention to you is something that we call a critical number. So I'm going to go through the definition of a critical number very particularly. So A is a critical number if the following happens. So the first thing is you have to have a function, and your function has to actually exist. It has to be defined there. It has to be in the domain. So it has to actually exist for f of A. Okay, then there's two conditions. When we look at the derivative, f prime at A could be 0, or the B part, the other thing that could happen with the derivative is it might not exist. So I'm going to write D and E for does not exist. So there's three things to think about. So first of all, is the number actually in the domain? So maybe we could write that as like point number 1. If I just kind of sketch this definition. And then point number 2 really comes in two parts. It's an either or situation. Either the derivative is 0 or it doesn't exist. So if you put all of those things together, this is the definition of what we call a critical number. So I'm going to write that down. So then we can say that A is a critical number of F. So notice that we say that altogether in the language, it's included that A is a critical number of a function. So we don't just say 5 is a critical number or 12 is a critical number. We would say that here's a function, let's say x squared, and you might say 0 is a critical number of x squared, the function x squared. Okay, so that's very important to understand exactly what we mean when we say critical number, because we're going to then use critical numbers later on in the course and in multiple different areas of the course, in curve sketching, and today when we do the closed interval method, I'm going to say the word critical number, and it's very important that we know that that's what we're actually talking about is this very specific definition. So if you're testing for maxes and mins, you have to look at particular numbers. So what you need to test is f of all the critical numbers and you need to also test f of the endpoints of your interval that you're dealing with. It should give you an interval. And we'll do an example right away. So f of the endpoints. And you test this for the largest value and the smallest value. And that will tell you the absolute max and absolute min. So the largest will give you the max, and the smallest will of course give you the min. Okay, so let's put this into action. We'll first find critical numbers of a given function. Okay, so our function here is ln x. I'm going to write the x to the power 2 in the denominator. So in order to find my critical function or critical numbers, I first maybe just kind of think about the domain. I can plug in anything that's positive into ln. So my domain is all real numbers that are positive. Okay, and then I will look for places where the derivative is either 0 or doesn't exist within that domain. So f prime of x, using the quotient rule, I would get 1 over x for the derivative of ln, and then copy x squared, minus copy ln x, and then the derivative of x squared is 2x. And that all goes over x squared squared, so x to the power 4. So maybe a little bit of simplification is in order here. Maybe let's just move this aside over a little bit to give us some space. So I'm noticing that x cancels out right there with the numerator and the denominator, making just one x in the numerator. And then there's an x in both terms in the numerator altogether. So I can cancel one of those out. So 1x gets slashed away in the numerator and the denominator altogether. So the first term just becomes 1, and the next term becomes 2 ln x, and then I have x cubed left over in the bottom. Okay, so I'm interested in when this might be 0 or might not exist. So let's start with f prime equaling 0. So that would involve the numerator, 1 minus 2 ln x equaling 0. So that would mean that ln x would have to equal 1/2. And that would mean that x is equal to e to the power 1/2, or the square root of e. So that's certainly one possibility. So those are in my possibilities there. And they also have 0 as a possibility. So we have to question whether 0 is a critical number. Okay, now certainly the derivative does not exist at 0 because we can't plug in 0 into the denominator. But remember that it actually has to be part of the domain, and 0 is not part of the domain to begin with. So remember before I said there's two things we really need to check. We need to check that f itself exists, and we need to have one of the two conditions below. So if it's not even part of the domain of the function, then throw it in the garbage. We don't worry about it being a critical number. We wouldn't say 0 is a critical number of this function because 0 is not even a part of that function's domain. So C is the correct answer. It's just e and its square root of the critical numbers for this particular problem. Okay, so minimum and maximum values are now at our disposal. We have all the tools to deal with something like this. We just need to set up the test and find the absolute mins and absolute maxes. Okay, so the first thing that we're maybe interested in doing is finding the critical numbers. Or maybe even before we do that, maybe we'll just find the domain of my function. So, what is the domain of this particular function? So we have to make sure we're not plugging in 0 or negative values into ln. That's the only thing we're concerned about. One thing you can do to just kind of analyze that quickly, if you're concerned about that, is complete the squares. I like doing that because it tells me whether my parabola crosses the x-axis or not. So if we just complete the squares, I'm going to write down this structure on my page, and inside the brackets, the next number that I write down is half of the number that is the coefficient for x, so plus 1/2, plus 1 divided by 2, and then you subtract the square of what you just wrote down, and then copy the plus 1, copy the constant number that's there. So we have minus a quarter plus 1, and the key here is that just adds together to get 3/4. So I can write that as plus 3/4. And this particular expression is always positive. right? This particular expression must be positive because we're squaring stuff and then we're adding an amount that is positive. So the whole thing must be positive. This part is positive and that part is positive. And the reason why I wanted to just show that is because we're always plugging in a positive amount to ln. That means that my domain is all real numbers. So everything is a question of being a critical number or not. I don't have any numbers that are immediately thrown away. So the next thing I want to do, for finding critical numbers is move on to this step 2 and just kind of think about whether or not my derivative is 0 or possibly does not exist at certain points. Okay, so my f prime of x, we'll write this down on the page, is throw everything into the denominator. The derivative of a ln function is that in the denominator, and put in the numerator the derivative, so 2x plus 1. And then we will kind of recognize that there's no way to make the denominator 0 because we know that that amount is always positive. So the only way that we have a critical number here is if all of this equals 0. And the only way that that occurs is if 2x plus 1 is equal to 0. And that means exactly that x must be minus 1/2. Okay, so we have our test all ready to go. We have all our critical numbers. It's just minus 1/2. So we can test. We have the interval to test and the critical number to test. So let's start with smallest to biggest. Minus 1, I get 0. And if I plug in the critical number of minus 1/2, I get, I'm plugging in minus 1/2. Well, it's kind of nice that I completed the squares here. The minus 1/2 goes away with plus 1/2, and I just get 3/4. And of course, that is ln of 3/4. So let's make sure we get that right. Ln of 3/4. And then finally, f of positive 1. If I plug that in, I would get ln of 1, 2, 3. So ln of 3. Okay, so to find the absolute max and absolute min, it has to be one of these 3 points for either the max or the min. And to find the max, you just pick off the largest one. And to find the min, you just pick up the smallest one. So let's remember that ln values take us into negative land for anything that's less than 1. So that has to be the min, because that's actually a negative number, so it's less than the 0. And that makes ln 3. It's a relatively small number still, but it's the max on this domain for the function that's given. So our answer becomes B. The ln of 3/4 is the min, and the max is ln 3. Okay, a couple more problems for us today, and then we'll answer some questions. Okay, so this one, very similarly, we follow the same test, the same strategy as before. This one is a little bit clearer that the domain is all real numbers. So I'm going to, again, just kind of write that down to remind ourselves that we at least thought about it. So the domain is every real number. And from here, we're just interested in taking the derivative. So my f prime of x is pull the 3 downhill. So write the 3 and then copy everything that's inside the brackets, which is x squared minus 1. And then take the derivative of the inside, which is 2x. Oh, I need to drop the power by 1, so that's a 2. And then there is no values where this derivative does not exist. So I just need to set this equal to 0 and solve. So they're all nice and factored for us. We can find these x values by looking at each of the individual factors of how they become 0. So x could equal 0, or if we plug in either a 1 or possibly a -1 into the x squared, we'll also get 0. All right, so now we're ready for the test. So we will test out all the critical numbers, and we will test the endpoints of our interval. Okay, so f, I'll pick the smallest one first, maybe -1, and I'll plug that into the function. And actually you get the same value if you plug in +1, so maybe I'll cheat and plug both of them in at the same time because you get the same answer out of the deal, which is 1 - 1 all cubed, giving you 0. And then f at 0, that's the other critical number. If I plug in 0, I would get -1 cubed, which would give me -1 overall. And then f finally of, what's the other number, 2, plugging in 2 would give me 4 - 1, which is 3, so 3 cubed, which gives me 27. Okay, so looking through this number right here, -1, that's my min. And the biggest one, that's my max. So the answer is D, -1 min, max 27. All right, one last problem for today. I think we have just enough time to complete this one. We're supposed to decide if the following function is continuous or discontinuous at point A. Okay, so this really just recycles some of the things that we talked about today. If the function is defined and it's part of the domain, then it's going to be continuous at that part of its domain. So yes, we can plug in 1 to this original function and you get like 0 out of the deal. But that's perfectly fine. That doesn't create a discontinuity. So I'm going to say that that's continuous. We're supposed to ask the same question for each one of these. So maybe I'll just write an A right there for the first one. And just evaluate it at 1 and notice that it is continuous. Same thing for the next one. You can just evaluate the function at 4 and notice that, okay, we'll get some number in the numerator and some number in the denominator. We don't even need to calculate these exact numbers. We're only really concerned with getting 0 in the denominator, and that didn't occur here. So this is also continuous, so A for continuous. Maybe we'll play the devil's advocate here. If we had A equal to 5, if that happened to be the case, then we would have a discontinuity. And we could evaluate, well, which type of discontinuity would we have? Well, if we plug in 5 into the numerator, we wouldn't get 0. It would be something other than 0. If we plug in 5 to the denominator, we would get 0. So you would have a infinite discontinuity. So under that devil's advocate case, you would get D. So if A equaled 5, then the answer would be D. Okay, so the next one, if we plug in 9 right there, we get the square root of 9, which is 3, so 3 minus 3, and that's exactly the scenario that we just talked about. We get D as the answer for a infinite discontinuity. So that's once again the case where you have a number over 0 and that number is non-zero in the numerator. The last example, every value for an exponential function is non-zero. You can get close and close and close to 0. So certainly when we plug in 0, that's no problem. e to the power 0 is just 1, and you get 10 out of the deal. So that's another case where it's just continuous. So remember that the removable discontinuity might come from a case of having 0 over 0. That didn't occur in any of these examples up here. And the jump discontinuity could come from a piecewise function. And there just wasn't any piecewise functions here. Okay, so that finishes our lecture for today. Thanks for watching all the way to the end. Appreciate you, and we'll see you on the next one.